Hi, my name is Jackson Dill, and this is my presentation on the optimization of offshore energy production through a blended wind and wave model. So, why clean energy, and why should you care, and what motivated me to do this research? Carbon emissions have risen almost 60% in the year of 2023, and during that same time span, the electrical demand rose almost 36%. And as of then, only 21% of the United States' total energy production came from renewable energy. And so this big picture looks pretty rough. And if these conditions continue, eventually we'll run out of energy, or we'll have a serious energy demand that cannot be met. And so trying to meet this with clean energy is super important as we progress into the future. So this is where offshore wind comes in. Wind energy is currently the largest source of clean energy in the United States, so therefore improving this larger chunk will hopefully lead to a significant increase in clean energy. However, wind power is super inconsistent because obviously the wind's not going to be blowing at maximum strength the entire time, which is why I think wave energy converters would be well paired with this technology. Being super consistent is important when running an electrical grid because obviously people need energy throughout all of the day and all of the night and throughout the entire year. And so if the wind isn't blowing and then you have no energy production, then that leads to some serious issues. And so I'll get into this a little bit later, but that's kind of why consistency is important. Also, for the rest of this presentation, FOT will stand for floating offshore turbine, and WEC will stand for wave energy converters, just to kind of help you out and understand what I'm saying. Those are what those mean. And so to give you a little bit of a picture as to what these technologies are, if you don't know what they are off the top of your head, on the left we have the Pelamis wave energy converter. So it's 390 feet long, and the way it produces energy is when the waves flow, those segments in this technology bob up and down, and in the middle they're connected with this piece, and as that bobs up and down, it shifts this centerpiece up and down to generate energy. And then on the right, this looks like a typical turbine you would see on land, except for it's floating out in the ocean, and it's about 367 feet tall. And both of these models are the ones that I'll be using for the remainder of this study. And so then I explained why wind energy, but let me get into a little bit more of why wave energy is important. So these graphs from Stoutenberg et al. In 2010 over here kind of show you the consistency of wave energy throughout the day, month, and year. And that's super important, like I mentioned, because providing consistent energy is how you can just solely rely on renewable energy. Because currently we have to rely on non-renewable energy because we need energy all the time, and so being able to consistently provide energy through a renewable source is how you can actually switch to just entirely renewable energy, which is eventually the goal. And then also using wave energy technology with wind energy technology allows us to share certain electrical components. And those can be super expensive, and you have to translate or transfer your energy back to shore, obviously. And so being able to share those means it's a little bit cheaper if we combine both of these. And then also wave energy converters also do actually produce energy like in their name. And so this is also a benefit of using this technology. And then these two graphs here from Mills and On show wind and wave energy respectively, and their LCOE, or basically it stands for levelized cost of energy, but it's just a metric of how successful this technology would be if you implemented it in this location. And for the left, as you get to the more yellowish areas, it's hypothesized that wind technology will perform well. And then on the right graph, as you get to the reddish areas, it's hypothesized that wave energy will be super successful. And these graphs don't exactly look the same, but basically, if you overlap them, the areas in which they seem to appear to be successful are pretty similar. And you might have already thought of this, but wind drives the waves. And so if it's super windy outside, then typically the waves will also be very strong. And so this kind of creates a correlation. And you can expect that if the wind is very strong, the waves will also be very strong. So hopefully this will lead to our best spot to put a wave and wind farm. And so for a little bit of gap, currently there's a lot of research into floating offshore turbines and wave energy converters separately, but the pairing of the two is extremely limited. And then especially for the eastern United States coast, there's virtually no research done for this. And then also creating some sort of site-specific optimization, so for pinpointing locations on the U.S. East Coast using actual weather data to create some sort of financial viability to compare it to just current energy production has not been done a whole lot. So hopefully we can bridge some of this gap. And then the goal for me specifically was to improve offshore wind technology by pairing it with wave energy converters and then hypothesizing and calculating the most optimal location for a wind wave farm on the East Coast. and then also simulating some sort of stress test to make sure that our turbine and wave energy converter models will hold up to the environmental conditions that we're hopefully placing them in. And so just to remind you, these are the locations along the East Coast that are hypothesized to be really good, and then some that are hypothesized to be not so great. And so in order to just kind of get a full picture of this, I chose some sites that will hopefully give us a full picture of what's going on. And so this here is a picture from BOEM, or the Bureau of Ocean Energy Management. Basically, they lease land in these little parcels and little kind of outlined weird-looking shapes along the ocean for research or energy companies to kind of research or actually put technology out in the ocean to generate energy or study, whatever they would like. And so this is important because this is where we're going to be choosing from. And it doesn't really make sense to choose an area that's not in one of these, because realistically, we're not going to be able to implement technology there if we're not allowed to by the government. So this is kind of what we're stuck choosing from, which isn't really all that horrible because we do have sites from so many different states and different areas. And so the ones circled in red here are the ones I chose, and we just did 5 for the study. And the numbers will correlate to graphs and other information as you get further into this presentation. I'll kind of remind you for at least the best site where that is, but if you're really interested and you need to come back to this slide, these are the numbers and the sites they correlate to. And so basically, since I don't have the time or the availability or the ability to go out and get weather data myself all along the eastern United States coast as a high school kid, the next best option is getting other people's weather data from the internet. And so ERA5 is just a public weather database that has weather data for almost every single day for years and years. So this is super helpful because I can get the locations from BOEM and then the weather data that ERA5 has at those specific locations to use later in my research. And so if you're trying to replicate this yourself, these are the different data formats and variables I took from this website and the time span I took. And so for the time span, at least, this is kind of the hypothesized best time of year for wind and wave. It's when they're the strongest most consistently. And I chose this time span so that we could hopefully get like the best and strongest picture of this technology to see, how well can it compete against other technologies. And the rest of this is just kind of general ways of gathering weather data, well accepted ways of doing that. And so this is what the data looks like after you get it. And these graphs might look confusing. Why there's a corner chopped out of the top left and what all these colors mean and these numbers. But basically, these two graphs go together. And I did this for all of the different environmental data I need to calculate these things. But the most important thing is in the right graph, the top number is kind of the general averaged value at that location. And so obviously, if you sit out in the ocean and you measure the wind speed, it's not going to be the same all the time. But the topmost number is kind of the averaged or expected amount, which is the most important part of what we're going to be taking away from this weather data. And so why do we need this weather data and what can we use it for? So we're going to input it into power curves, which are basically little curves produced by wind turbine or wave energy converter companies that allow you to estimate electrical output based on the weather data you input. And so it's really just easier if you look at it. So this is the power curve for the Pelamis wave energy converter, which is the one for our study, and then the weather data I got for site 1. And so if you just follow along the axes for wave height and wave period, and then just find where they intersect, that's the amount of energy it is hypothesized to generate. So obviously, if the waves aren't that strong, towards the top left, you're going to have 0 energy output. And then if they're really, really raging, then the bottom right is kind of the larger values that you can expect. And similarly for the same thing, but just with wind speed and air density, if the wind speed is super high and the air is super dense, then you can expect a lot of energy. And if it's not, then you can expect very little energy. And so I repeated this process. I didn't really show it to make this presentation more quick, but you repeat this process for all the different 5 sites and then get those energy values, and that's what you can expect hypothetically to generate at those specific sites. And so here's some graphs of all of this put together. So the wind energy by itself for sites 1 through 5, measured in gigawatts on the y-axis there, and then the same for wave energy in gigawatts on the y-axis. And if you notice, the numbers are much larger for wind energy, and that's to be expected. It does produce more energy than wave energy. But also, if you kind of notice, sites 1 and 2 and 3 and 4, they all correlate in terms of what has the most and least energy. And like I said, this is typically due to the fact that wind creates waves, and so you would expect those to go hand in hand. And it's good that they did, which means that our data is hopefully right. And then for annual consistency and capacity factor, this is basically just showing how efficient it is. So if something has a capacity factor of 1, then it's doing great and it's being as efficient as it can be. And so as you can see, wind is shown on the left and wave is shown on the right. And basically this is just to prove that the capacity factor for wave is more stable than wind, which is like we thought it would be. And then all of this data leads us to find that the site number 1 near Massachusetts is the most optimal site. And this is kind of the region from our preliminary data or background data that also was thought to be most beneficial or the best. Is we're confirming that that is true, and that's what's been found in the study. And so then kind of on a different light, the structural analysis, so to make sure that our models will survive, we modeled the turbine that we are using to simulate at a 1 to 13 scale in Fusion 360, which is just a CAD system. And then we simulated 20-mile-an-hour winds, which are the winds that were expected in this location or could be expected. And that's also the turbine blade and this cool little animation we made down here in the bottom right of the turbine spinning. Pretty proud of that. But here's the structural comparison. So there's 3 different turbine models just to kind of make sure we're covering all of our bases and see what's the best. And so we simulated these with 20-mile-an-hour winds. And as you can see, the turbine on the right here shows the least amount of deformation, which means it's going to hold up the most. On the right here, hold on, let me move myself so you can see it, is CFD for this red and this other model here. And basically, as you progress further out into the blade, it goes under more duress, which is to be expected, but it's not breaking. And then also this design and shape here kind of just shows you that this is aerodynamic and it's catching the wind where it's supposed to be to create more torque and energy generation like we want it to be. And so then basically what does this mean? As expected, wind power is significantly more than wave. And then some sources of error could be this ERA5 database isn't foolproof and 100% guaranteed accuracy. So there could be some issues with that. And then also we can't account for the unaccountable. And so if maintenance needs to be done or, some unforeseen issue happens, we can't really control that. And so it's, of course, a simulation project and it's not 100% guaranteed that it will generate the energy that we're simulating. And then here's some more CFD, and basically this is just showing laminar flow and how it produces torque. Basically, the darker the colors, the more force on the blade. And where we want the force on the blade, there is force on the blade in this red area here. And where we don't want it so that it won't break, there's like the lighter colors. And basically this is just showing that it's super aerodynamic and exactly how we want it to be. And then the economic viability measured in dollars per gigawatt. Yeah, so this is showing our optimal farm design site 1, and then natural gas, which is the most commonly used energy generation tool in Massachusetts, just to stay relevant. And as you can see, natural gas is super consistent because you're just doing a controlled energy generation, in a lab or in a plant. So it's going to stay constant. But as our weather factors change, those obviously are not controlled and do not stay constant. And so the price changes as we become more or less efficient. And as you can see, there's a super big gap, and it's very expensive to produce. It makes much more sense monetarily to make natural gas instead of renewable energy. And that's the unfortunate part of renewable energy, is that it's not efficient enough yet and it's super expensive. And that's the goal of this research, is to hopefully lower that in the future. And as natural gas becomes more scarce and we run out of these materials, hopefully eventually it will become beneficial to use renewable energy. And then this is also showing the capacity factor for wind, wave, and natural gas. This is once again to show that waves are more consistent and don't change as much as the wind does. And then it's hard to kind of see this natural gas line at 0.6 capacity factor is just showing that it's constantly operating at the same rate because it's controlled and is intentionally made that way. So it's more efficient than wind and wave will be, unfortunately. But as we improve technology, hopefully it will close the gap in capacity factor as well. And so as I continue my research, I hope to add more sites along the East Coast and use more advanced power curves to get a full and better picture of weather data and be able to have increased accuracy in what I'm estimating, and then continue to run the cost analysis so that as things update and technology becomes better, we can kind of see if the gap is closing between these two technologies. And then also just to experiment with more turbine models and converter models at different price points to include all different kind of farm designs and budgets and be more inclusive so my data is more applicable to different experiments and locations. And then also to improve other aspects of these technologies, but make them more competitive and maybe have the higher chance of implementing them in the future. These are my references. Thank you so much.